let's continue with the Kerr metric. So the last thing I did was that I taught a little bit about the possible route towards Kerr metric. So I abstained from giving anything like a derivation. Actually, if you want to see a derivation, I think I already told you that you can find it, for instance, in Chandrasekhar. He is taking this route, which actually was also the historical route, how the Kerr metric was found, namely using this so-called Newman-Penrose formalism, which is closely associated with the eigenvalue problem of the Weyl curvature tensor. But these are things which would take too long to do here in this course, so I'm not going to do. I'm not going into this. So in whichever way you arrive at the Kerr metric, finally we will have it, and we will now discuss it in some detail. And actually the form in which I gave the metric and in which I will discuss them for the most time is not the form in which Kerr actually had given it. It was found in this form with the coordinates r, theta, phi, and t by two other gentlemen by the names of Boyer and Lindquist. So what we discuss here is a Kerr metric in Boyer-Lindquist coordinates. I think I forgot to mention this name last time. In Boyer-Lindquist coordinates. So they look like ordinary spherical polar coordinates. So they are denoted t, r, theta, and phi. And they are adapted as closely to the symmetry of the spacetime as one can do it. So for any calculations that are related with the symmetry of these spacetimes, this is certainly the best way of writing the metric. For other purposes, other forms might be more appropriate. Okay, and the metric reads like that. So we have, there are a few abbreviations. I will explain them in a minute. 1 minus 2m over rho. 2mr over rho squared dt squared plus rho squared over delta. I tell you in a minute what delta is. dr squared plus rho squared d theta squared plus sine squared theta bracket r squared plus a squared plus 2mar sine theta over rho squared d phi squared. And then there is a cross term. That's a new feature which we didn't have in any of the metrics which we have been talking about, that actually the metric must have an off-diagonal term. So we cannot write it in diagonal form. So we have a dt d phi term. So I should tell you what the abbreviations are. We will use them constantly in the following. Rho square, I think I had already mentioned last time. This is, r squared plus a squared cosine squared theta. And delta I have now introduced as an abbreviation for r squared minus a squared plus 2mr. So the coordinates are t, r, theta, and phi. And rho squared and delta are just abbreviations for these expressions. So you see the only parameters which are in the metric are the m and the a. So it's a two-parameter family of metrics. So the Kerr metric, let me write it this way, depends on two parameters. Little m and little a. And the interpretation comes from comparison with a far field. So if you go far away from the center, so if you go to the region where r is very big, then also for this metric, you see that the metric approaches the flat metric. So this spacetime is also asymptotically flat, as one says. So for big radii, it approaches Minkowski spacetime. And then you can compare the leading order coefficient with the Newtonian theory. And what you find is that the m is just what earlier we denoted by rs half. So this would be the mass of the body times the gravitational constant over c squared. So in the following, when we work with the Kerr metric, I will always use this symbol little m instead of the rs, because as you will see in a minute, the horizon has nothing to do in the Kerr metric with the value of rs. So there's actually no particular reason to consider this quantity rs for a rotating object. So I will then always consider this little m here, which is a length. Yeah? Keep this in mind. Little m is a length. It's related to the mass in true units, which we have to use nowadays by this equation. And the other parameter is the a. And the a, well, if you remember the way in which I've approached the Kerr metric, from this way it was clear that it has something to do with the rotation. Yeah, because it was introduced as a parameter which flattened the coordinate system. So if you analyze the far field, so you can do something like a monopole expansion for this metric. Then for the mass monopoles, you have for the mass multipoles, you have this as a leading term. So this gives you really the mass monopole, which is called the mass. And you can also do an expansion for the angular momentum. And then you will see that the A gives you the specific angular momentum. If you want to have it in proper units, I need, so it's roughly speaking, where is it? I've noted it. I've took this down somewhere because I can never, oops. The J over MC? Yes, here, J over MC. So J is the angular momentum in proper units, and I divide by mass. This is what one would call the specific angular momentum. Angular momentum divided by mass. And in order to make it into a length, I put a C in the denominator, and then also A is a length. You see, A and M must have the same dimension. Yeah? A is also a length. You can read it here, for instance. So actually, just by dimensional analysis, you see that if you want to make the J into a length, that you have to do it by this combination. But in order to know that there is no factor 2 or 4 or something like that in front of this, they would actually have to analyze the far field to do this multipole expansion. So to be sure that A is precisely the geometrized specific angular momentum and doesn't deviate by a certain numerical factor. So these are the two parameters. So we have an object which has a mass, and we have an object which has an angular momentum. And the angular momentum is associated with this cross term. You see, the dt d phi term is associated with the parameter A. So if we set A equal to 0, then this term is gone. Yeah, we can write this here. What happens for, if we say end to 0? If we say send A to 0, well, if you do this and take this into account, you will see that you get the Schwarzschild metric. So the Kerr family of metrics contains Schwarzschild as a special case. So if a thing is not rotating, it has no angular momentum, then we get Schwarzschild. And if we send M to 0, if you do it, then you get precisely the expression from which we started last time, namely Minkowski spacetime in spheroidal coordinates. Then we get Minkowski, the flat spacetime, in spheroidal coordinates, not in standard spherical coordinates. Yeah, the A is a measure for the deviation of the surfaces are equal constant from spheres, spheroidal coordinates. Okay, so I said already that the A is associated with the cross term, and maybe it's worthwhile to emphasize what this means. So if we have such a cross term, what does this mean? If you have the hypersurface T equal constant, where the hypersurface T equal constant is spanned by the vector fields d by dr, d by d phi, and d by d theta, they are linearly independent. Yeah, I cannot properly draw this, because I cannot draw a 4-dimensional picture, but you should try to imagine these three vectors as being linearly independent. So they are tangent to the surface T equal constant. Now we have a cross term, a dt d phi term. This means the coefficient here is gt phi, right? Gt phi is not 0. This means the vector field d by dt is not perpendicular on d by d phi. So this angle here, this is not a right angle. Yeah? So the vector field d by dt is not perpendicular to the hypersurface t equal constant. And if you draw this at each point, if you draw this vector at each point and take into account that the coefficient depends only on r and theta, not on phi, then you get something which goes in this way around the circle. So the t lines have, because of this cross term, they have a kind of twist. Yeah? So they are not perpendicular to the hypersurface t equal constant, but they have a certain twist, like spaghetti on a fork. Yeah? So they go up in this way. And this is a characteristic for the gravitational field of rotating objects. You must have such cross terms when you have a rotating source. Yeah? So of course you can always introduce coordinates which have cross terms, yeah, which are not diagonal if you want to do so. But if you have a rotating object, then you are forced to do so. You must have these terms. Okay, and we distinguish this by saying that this space-time is not static, it is stationary. Yeah? If the vector field d by dt would be perpendicular to the surfaces t equal constant, then we would say the space-time is static. Yeah, the coefficients do not depend on t, so we have a symmetry in the time direction. And if d by dt would be perpendicular to t equal constant, then we would say the space-time is static. So Schwarzschild is static, Reiser-Nordström is static, Keutler is static. But here we have this cross term, and then we say the space-time is stationary. So stationary means just the metric coefficients are independent of t, but it allows for the fact that the vector field is not perpendicular to the hypersurfaces. Okay, so that's the first observation. Then the second observation. Yeah, we should talk about the range of the coordinates. Well, if we work with such coordinates, which we denote t, r, theta, phi, we are used to working with spherical polar coordinates, and in these coordinates, of course, these spatial coordinates cover just our three-dimensional ordinary Euclidean space, and r equals 0 is the origin. Yeah, that's what we are used to. But if this metric is really in agreement with this interpretation, it has to be checked. Namely, we have to see if r equals 0 is really a point in the metrical sense. We can read this from the metric. How can we do this? We consider the spheres, r equal constant. Yeah, r equal constant and t equal constant. So they are just parameterized by theta and phi. And we look at these spheres, and then we shrink them. So we send r to 0. And the question is the area going to 0 or is it not? If it does go to 0, as it does for Schwarzschild, then r equals 0 really is a point. But if it does not, then r equals 0 is not a point. And this gives a completely new feature. So, range of the coordinates. So there's no question about t. T runs over r. Why not? Yeah, we would. There's no reason to cut the t coordinate somewhere. The coefficients do not depend on t, so we can consider the space-time for all t. Theta and phi are our usual. Let me write it in this way. Here they parameterize the two-sphere as we are used to it. Yeah, they are standard coordinates on the two-sphere. But with the r coordinates, if you think that r runs from 0 to infinity, then maybe you will be surprised. So r coordinate. In order to discuss this, we consider the spheres RT equal constant. And we look at the metric of this object. We can read it from this form of the metric. So, oh my goodness. So if r is equal to a constant, then this is gone. And if t is equal to a constant, these two terms are gone. Yeah? We don't go in the direction of increasing or decreasing t. So this is gone, this is gone, this is gone. And let's see what's the metric on this two-sphere. It's a metric on a two-dimensional manifold, parameterized by theta and phi. Let me denote it in this way. And you can read what the metric is. So the first two terms are gone. Then we have rho squared d theta squared. And we have the d phi squared term. R squared plus a squared. plus 2mar sine theta over rho squared. Okay, let's write this out. So what was rho squared? Was r squared plus a squared cosine squared theta. And here also I have the rho squared in the denominator, r squared plus a squared cosine squared theta d phi squared. And now let's see what this metric is doing for r to 0. So then we have a squared cosine squared theta d theta squared plus this gives an a squared cosine squared theta in the denominator, but here I have an r. So this is also gone. I only have an a squared sine squared theta d phi squared. So we see for a equals 0, this metric degenerates completely. Here then it just gives 0. So that's the Schwarzschild case. In the Schwarzschild case, this is really, it degenerates completely into a point. But if a is different from 0, this is a perfectly regular metric. Yeah? So this is not a point. It is a sphere with a certain area. So for instance, we can calculate the length. Yeah? So for instance, if we have here the sphere r equals 0, if we consider such a circle of constant latitude, say theta, theta, and I want to calculate the length of this circle, then I can read this. So length of circle of latitude theta, you will see that it is not 0. Let's call it L. It's an integral over dl, and L is a coordinate which runs over this circle. So if I am on the circle, theta equal constant, then this term is not there. I only have this term here. So this gives me the length squared, right? So I have to take the square root, a sine theta d phi, and phi of course runs from 0 to 2 pi, and that's of course not 0. So this is 2 pi a sine theta. It is 0 at the poles. Yeah? If theta is 0 or pi, then it actually is 0. Fine, this is a point, of course. Yeah? But for all other circles of latitude, this is not 0. So this sphere really is a sphere with a certain area, and the circles on this sphere have a finite length. So it's not a point. And yeah, this opens a new and intriguing possibility. If this is true, if this is not a point, if this is really a sphere of finite radius, this means that in principle one could cross from the outside to the inside. Yeah? We cannot move through the point r equals 0, neither in Minkowski space nor in Schwarzschild spacetime. In Minkowski space, it's just a point in three-dimensional space, and there's nothing behind this, so to speak. In Schwarzschild spacetime, it's even a curvature singularity, so we cannot even, we don't even know what happens if we approach this point. But here, it's a regular sphere, and we can cross through it, and this means we have to allow the r coordinate to take negative values. Yeah? So we come from the region of positive r, we see at r equals 0, we are at a perfectly regular sphere, so why shouldn't we continue towards the region of negative r? And that's what we are doing. So the r coordinate has range from minus infinity to plus infinity. So that's something which is a little bit unusual if we work with spherical coordinates, but we have to acquaint ourselves with this. So the r coordinate, so the r coordinate also runs over all of r. Well, there's one thing, of course, we have to make sure. I've just looked at this angular part, and I've discussed only the metric of the angular part. Of course, we have to make sure that the other metric coefficients do not play some tricks on us on the sphere. Yeah? So, for instance, if the other metric coefficients would produce a curvature singularity on the whole sphere, then of course we couldn't cross it. Yeah? So this has also to be checked. We will do this in a minute. You will see that there is a singularity of other metric coefficients, but only on part of the sphere, not everywhere. So the statements that we can pass through it remains still true. So the range of our coordinates is the following. T runs over R, theta and phi run over spheres, and R runs over all of R. So then the next thing is singularities of the metric. So as this is a generalization from Schwarzschild spacetime, we will expect that also here metric singularities occur in the metric, and we see this immediately. If rho square is equal to 0, I have a, yeah?
Just a short question concerning the metric coefficient in front of the d phi squared. So in the second row.
Yeah.
I'm trying to add up the units. So r squared is length squared, plus a squared is length squared,
right.
MAR is length cubed, over rho squared is length.
You're right. Something is wrong with that.
One more length. Maybe r squared.
Yeah, it's an a squared. It's an a squared. Thank you. It's an a squared here. But I think this should also be wrong here. Then, yeah, it's an a squared. Yeah, okay, that's an interesting feature. We see in all these expressions we only have a squared. So the sign of a doesn't matter for these terms. That's the only point where we have an a. So you see, if you change the sign of a, you can compensate this by changing the direction of the phi coordinate. So changing the sign of a corresponds to changing the sense of rotation. Yeah? So, and for this reason, there should be no a in this term. Thank you very much. This was of course wrong. Okay, singularities of the metric. So we look at the metric coefficients and we see rho squared equals 0 is some kind of singularity. It's a 0 in the denominator, and delta equals 0. And delta equals 0. And we have to discuss this. Well, the first indication of what's going on at these points might come from comparison with Schwarzschild. So for Schwarzschild, or let's write for a to 0, rho squared equals 0. Rho squared is r squared plus a squared cosine squared theta. So this condition, we write it this way. Rho squared goes to r squared. Yeah? At r equals 0, that's a curvature singularity in the Schwarzschild spacetime. So this is, well, we expect that this will also be a curvature singularity in the Kerr spacetime. And, well, this can be verified by just calculating curvature invariance. So if you calculate the curvature invariance, you will see that at rho squared equals 0, actually, they will blow up as they do in the Schwarzschild spacetime at r equals 0. Well, and rho squared equals 0, what is this? Rho squared equals 0. If I draw again the sphere r equals 0, then I see that this is exactly the cross-section with the equatorial plane. So it's a ring in the equatorial plane. So rho squared equals 0 is equivalent to r squared equals 0 and cosine squared theta equals 0. This means theta is pi half. Yeah? So we have this singularity, which in the Schwarzschild limit approaches r equals 0. Yeah? So in the Schwarzschild limit, this whole sphere becomes a point, and then this ring becomes, let me indicate it in this way, this ring becomes becomes the point-like Schwarzschild singularity. So this still is a curvature singularity. So we cannot cross this ring, but the rest of the sphere r equals 0 is regular. So we have two hemispheres through which we can move from the region of positive r into the region of negative r. Yeah, they are sometimes called the throats of the Schwarzschild spacetime. Yeah, so it's comparatively narrow. R reaches, and then it widens up again if you're on the other side. So you go through this narrow region, and then you enter into a new world of negative r coordinates, and then you can move out again up to infinity, r equal minus infinity, if you like to do so. So it's like going through a throat, through a narrow bottleneck or something like that. Okay, so that's the first kind of singularity. So if you want to check what the character of the singularity is, what you would have to do is you would have to calculate the curvature tensor. I will not do this on the board because unfortunately the curvature tensor of the curve metric is a little bit more complicated than for Schwarzschild, for instance. Okay, so that's the first kind of singularity, and then we have the other singularity at delta equals 0. So what is delta equals 0? So delta, if I consider again the Schwarzschild limit, what happens to delta if I send a equal to 0, then I have r squared minus 2mr. So this gives, this is r squared 1 minus 2m over r. So either I am at r equals 0, that's a case we have already discussed up there, or we are at, no, what am I doing here? Squared.
Your sign is different in the delta on the upper board and on the lower board. So there you said delta is r squared.
Yeah, this was nonsense. Sorry, excuse me. It was a writing mistake. That's what I meant. Of course, I want to have the 1 minus 2m over r, which we are used to from Schwarzschild. So I need a minus sign here. Sorry, this was a writing mistake here. So apart from the case r equals 0, which we have discussed, also by the way, the delta in the denominator comes with a rho squared in the numerator. So this would, for r to 0, this brings an r square also in the numerator, right? So this r squared here in the denominator cancels with the r squared here. So r equals 0 is of no relevance for this consideration. So we have in the Schwarzschild limit this as 1 minus 2m over r, and that's where we have the horizon. In the Schwarzschild case we have one horizon, and we will see in a minute that in the Kerr case we will have in general two horizons. So yeah, just by analogy with the Schwarzschild case, you would expect that delta equals 0 give horizons. And actually, again, one should check this, and the way we actually will check this is that we will discuss the light rays in the space-time, and then we will do something very similar what we have done for the Schwarzschild space-time in order to see that you can extend the metric through these coordinate singularities. So we will see a little later that our suspicion that this is a coordinate singularity and that it can be remedied by coordinate transformation, we will actually work this out when we introduce the so-called Kerr coordinates, in which Kerr had found the metric. So he had found the metric in a representation where we didn't have these curvature, these coordinate singularities. Okay, so delta equals 0 is what goes to the horizon from the Schwarzschild case. But as I said already, in general we have not one horizon as we have in Schwarzschild. So delta equals 0 is, what is delta equals 0? It's r squared plus a squared minus 2m r equals 0. That's a quadratic equation for r. So in general it has two solutions. So let's solve this. So we have r is, let me write it this way. R plus minus, the solution of this equation is here. From this coefficient I have to take minus 1/2, so this gives an m, and then plus minus root m squared minus a squared. So we see we have two real solutions if a is smaller than m. I have a double zero if a is equal to m, and I have no real solution, neither positive nor negative, for a squared bigger than m squared. And while these three cases they are distinguished, I'll write this down in a minute. So in the first case we say, because there's a horizon, we say that we have a black hole. And if there's no horizon, if a squared is bigger than m squared, and we say that we have a naked singularity. So if a squared is smaller than m squared, so this would be a comparatively slowly rotating object. So in particular this is true for, let me write strictly bigger than 0. because otherwise I would also have only one horizon. Then I have two horizons. And where are they? Well, both solutions are real and positive, right? Because this is smaller than m squared. This means what I subtract here, in the case of the minus sign, is smaller than the m, so it's still positive, also for the negative sign. So I have 0, then r minus, and then r plus. If a squared is equal to m squared, then I have 1, as one says, degenerate horizon, which just means that it is a double zero, degenerate. And where is it? At r plus equal to r minus. This is just m. Yeah. So it is half the value of the position of the horizon for Schwarzschild. Yeah, for Schwarzschild it was 2m, if I use this little m notation, and this degenerate case is at r equal m. So that's what one calls the black hole case. And this is what one calls an extremal black hole. Yeah? So if we crank up the spin of the object, then in the beginning we have a black hole, and if the spin reaches some particular value, namely this value, then the two horizons come together, and for a squared bigger than m, a can be positive or negative, right? That's the reason why I always write it in terms of the squares, because we want to have black holes which rotate in this way and also black holes which rotate in the other way. So a can be positive or negative. Then we have no horizon. But we still have the singularity, the ring singularity, and that's what one calls a naked singularity. So if an object rotates very quickly, and then it will not collapse to a black hole, it will collapse to a naked singularity. And actually, I've given you the m and the a in terms of the mass and the angular momentum. If you insert here numbers for some celestial objects, for the Earth, for instance, if you insert the mass of the Earth and the angular momentum of the Earth, you find that a is considerably bigger than m for the Earth. So if the Earth would, just as it is, without losing mass or energy momentum, if it would collapse into a naked singularity, not into a black hole. Don't worry, this will not happen. But it just, if we imagine the situation, then it would go towards a naked singularity. Actually, I emphasize that this is true only as long as the body doesn't lose any mass or any angular momentum during this process of collapsing. Actually, if a body undergoes gravitational collapse, it will lose mass and it will lose angular momentum. There will be something like a supernova explosion or things like that before the object collapses into a black hole. And during this process, usually angular momentum is lost. And that's the reason why there could be hope that actually under realistic assumptions, bodies would collapse to black holes and not to naked singularities. And that's the so-called cosmic censorship hypothesis by Roger Penrose, who formulated this already in the 1960s. He said, I conjecture that under reasonable physical assumptions, any body which would undergo gravitational collapse would end up as a black hole and not as a naked singularity. Naked singularity means, of course, that I can see the singularity, that signals from the singularity can come towards me. And that's something which worries people. As long as there's a horizon, as long as the singularity is hidden behind the horizon, then one could live with a singularity. But naked singularities are somewhat dubious, and many people don't want to have them. So that's the reason why many people believe actually that these naked singularities do not exist. I said this is a conjecture, that since the 1960s it is a conjecture. There are some theorems which go towards statements of this direction, But none of them is of the form that one would say, well, the assumptions would really be satisfied for any realistic collapse. So this is still an open question. If we can really formulate a theorem, if such and such assumptions are satisfied and they are reasonable, we assume that they are always satisfied, then we get a black hole and not a naked singularity. So this is still missing. Yeah, there's a question?
But why is a naked singularity that bad? What's the problem with seeing it?
Yeah. So the question was, why are naked singularities so bad? Well, the singularity is always bad. We are worried about this. Yeah, we don't really understand what's going on at the singularity. If it's hidden behind the horizon, then we could say, well, we as an observer, we are certainly not planning jumping into the black hole, and as long as we are standing outside, we would never see the singularity. So then one could live with it. I think that's the kind of reasoning.
So it's basically you can ignore it.
Yes.
Yes.
Well, strictly speaking, actually, one cannot ignore it because the theory, in principle, allows an observer to go into the interior region and then examine the singularities from close up. Yeah. So it's not our everyday physics. We are not planning to do this, but in principle, one could. The theory doesn't prohibit this. So I would say the singularity is a problem even if it is behind the horizon. But if it is not behind the horizon, then it's even a bigger problem. And the singularities, quite generally speaking, are a problem of this theory. And most people just think that this classical theory is not applicable in the immediate neighborhood of a singularity, and we need some kind of a quantum theory in order to understand what's going on near the singularity. But as long as we have a horizon, then it's not absolutely necessary to discuss this question. So maybe then we could live with it. So let me try to draw this.
I have another question. Is there another reasonable argument why A can't extend M, except for this censorship argument?
Yeah, so the question was whether there's another argument why A cannot supersede M. Actually, I think there is not. So what I just said is some indication that values of A bigger than M are even the normal case for non-collapsed objects. Yeah? So virtually any celestial object we observe in the sky has an A, well, not every, but many of them have an A which is bigger than M. And so from this point of view, one would actually expect that the case A bigger than M is not at all unusual or exotic. But if you look at black holes in particular, not at other celestial objects, but at black hole, then the case A bigger than M becomes questionable. And I don't see any other reason, from some other kind of argument why A should be limited by M. I wouldn't know any. Okay, so let me try to draw a little picture of the image as far as we have gotten it now. So we have here R equals 0. So this is for the case that 0 is smaller than A squared, smaller than M squared. That's the situation I try to draw. So here is R equals 0. Here is a singularity on this ring. So the inner region is a region R smaller than 0. So you could imagine, for instance, you could plot for the distance from the origin, you could plot e to the r, for instance. Yeah? E to the r would be finite at r equals 0, and the origin, e to the r equals 0, would correspond to r equal minus infinity. Yeah, r equal minus infinity would then be here at the center. Yeah, let me indicate this in this way. So this would be e to the r, or if you like, e to the r over m to make it dimensionless in the exponent. Yeah. So that's the singularity, and then we have a horizon here, r minus at some radius, and we have another horizon, r plus here. And what happens in the Schwarzschild case? In the Schwarzschild case, a equals 0, you see r plus goes to 2m. So r plus then plays the role of our Schwarzschild horizon, which we are used to. And what happens to R minus? R minus goes to 0, if A goes to 0. If I M minus M here, this is 0. So R minus approaches R equals 0 in the Schwarzschild limit, but in the Schwarzschild limit, R equals 0 is a point. So in the Schwarzschild limit, everything inside the sphere becomes a point. It shrinks to a point. And so for Schwarzschild, we only have the region outside of R minus, which is then R equals 0. Okay, so this, and we will investigate, we will justify my claim that R plus and R minus are horizons later. So we will see how the light cones are situated here. So we will see that, that if I am here in this region, that I cannot get signals from behind the horizon R plus, and if I are in this region, that I cannot get signals from behind the horizon at R minus. So we will verify this when we discuss the light geodesics. Okay, so these were the singularities, ring singularity, which is a true singularity, and the horizon, which is a coordinate singularity. So what next? From Schwarzschild, we are used to the fact that the vector field d by dt changes its causal character at the horizon. We remember d by dt was time-like outside, and it became space-like inside. This is a little bit more complicated if the object rotates. So if the object rotates, there's also a surface where d by dt changes its causal character, but it does not coincide with the horizon. So there's a new characteristic surface which bounds a certain region, which is then called the ergo region, and which is associated with the question of whether d by dt is time-like. So let's investigate this question a little bit further. So the next thing is the causal character of our Killing vector fields of d by dt and d by d phi. So in the Schwarzschild spacetime, d by dt was time-like outside of the horizon, space-like inside, and d by d phi was space-like everywhere. We are used to the fact that phi is a spatial coordinate, the phi lines are always space-like. We would see that this is not everywhere the case in the Kerr spacetime. So we need to know where GTT is equal to 0. So we want to investigate if this becomes bigger than 0 somewhere. So this is a region where d by dt is space-like, so where I cannot stay on a t-line, where an observer cannot move along a t-line because he cannot move with superluminal velocity. Well, we can read the GTT. The GTT is what? So the boundary of this region, which is called the ergo region. Here's a region where this is satisfied. This is called the ergo region. Well, we can read it from the metric. So GTT is minus c squared 1 minus 2mr over rho squared. And on the boundary, this must become equal to 0. So what does this mean? Well, c squared, of course, is not equal to 0. We must have rho squared is equal to 2mr, and rho squared was r squared plus a squared cosine squared theta. It's 2mr. Well, let me write it this way. Write this on the other side. Then I have again a quadratic equation which I can solve for r. So I get r is m plus minus root m squared minus a squared cosine squared theta. And you see, if we are in the black hole case, where a squared is smaller than m squared, then we have always something positive under the square root. So this really has a real solution for any theta. So along the whole range of the theta coordinate, we have two values of the r coordinate where this is actually satisfied. So our ergo region has an outer boundary, which corresponds to the plus side, and an inner boundary which corresponds to the which corresponds to the negative sign. So I shouldn't denote this also r plus minus, because this would we would be confused with the horizon. So let me call this r tilde r plus minus. So r equal r tilde plus, this is the outer boundary, and r equal r tilde minus is the inner boundary of the so-called ergo region. And we can try to plot this. If we do it in this kind of picture, maybe I make a new picture. So if we do it in the standard plotting, where we use the r coordinate, then I have here my horizon r plus. Oops, this is supposed to be a sphere. So this is r plus. And you see, if I have cosine theta equal to 0, this means, no, sorry, equal to 1. If I compare with this expression, if I have cosine theta equal to 1, this means at the poles. Yeah? At the poles, I have the same expression as for the horizon. So at the poles, my boundary of the ergo region touches the horizons. But then you see, for on the equator, this here is 0. On the equator, I have a bigger value, because what I subtract here is smaller. On the equator, it's actually even equal to 0. So I have something like an elliptic deformation. So this is r equal r tilde plus. So that's the ergo region. And here in this region, I have d by dt space-like. What does this mean? It means if I'm outside of the ergo region, then I can stay on a t-line. An observer can stay on a t-line. But if I'm inside, if I have crossed this limit, this limit surface here, then I can no longer stay at a particular t-line. We will see that actually I can move at a constant r coordinate, but I need a phi coordinate. Yeah? If I move, if I have a d by dt component and a d by d phi component, this means I'm rotating around the center. This is possible at a constant r coordinate in this area, but I cannot just move on a t-line. This is impossible. So one sometimes says that inside the ergo region, observer must rotate. Yeah, he cannot just move on a t-line. And there's also an inner boundary, which I do not plot, because for an observer outside, of course, this outer region is particularly interesting. Yeah? So for an outside observer, only the region outside of R plus is accessible by any kind of observation. So the part of the ergo region which is actually of relevance for an observer outside at big radius coordinates is a region between this limit surface r equal r tilde plus and the horizon at r plus. This is sometimes also called the stationarity limit surface or something like that. So this here is called limit of stationarity surface or something like that. Yeah, it's the boundary of the ergo region. So that's a region where the vector field d by dt stops being time-like. So at least with respect to the vector field d by dt, the space-time is no longer stationary. That's where this name comes from. So if you use this representation, then the picture is a little bit deformed. So if you use e to the r, or e to the r over m for the radial coordinate, then you have, r equal constants means r equal constant, so the horizon is still a sphere. The horizon is still a sphere, but because the relation between the radius coordinate and the theta coordinate is now different from the old representation. This is no longer, has no longer an elliptical cross section. It is deformed in a certain way, and it's deformed in this way. So the ergo region, is deformed in this. Of course, symmetric. Everything's spherically symmetric. So this here is a region where d by dt is space-like. So this is R plus tilde.
But this is not only in the extreme case, right?
I'm sorry?
It's not only in the extreme case.
No, I'm in the sub-extreme case.
Yeah.
I'm in the sub-extreme case. So I also have here another horizon, which is irrelevant for the outside observer, but I have also an R minus here. Okay, so that was the causal character of d by dt. So that's a new feature, right? In the Schwarzschild case, these two surfaces coincide. Yeah, they join to the familiar Schwarzschild horizon. But here is a horizon, and here is what happens. Usually I like to quote from Richard Wagner's Parsifal. There's a line where Gronemann said, zur Zeit wird hier der Raum. Yeah, so space becomes time, and that's exactly what happens here at this surface. Yeah, the vector field d by dt, which is a time-like coordinate outside, which gives the way in which our time is running outside. This becomes a space-like, the T-lines become space-like. So space and time, one becomes the other. And here it's a little bit more complicated than in the Schwarzschild spacetime. In the Schwarzschild spacetime, everything happens at one surface. Yeah, space becomes time, and time becomes space, and this is also the horizon. Everything coincides. And here this is no longer coinciding. So here we have to distinguish this limit of stationarity surface and the horizon.
But if time becomes space, then we can go into the past, right?
Yes, in a sense. Remember what we did when we made the Eddington-Finkelstein extension? We had the possibility to do it either with the ingoing or with the outgoing Eddington-Finkelstein coordinates. So one is related to the other by an inversion of the time coordinate. Yeah? So we can really invert, we have to make the choice once if we do the extension over the horizon, and we can do it in two different ways. So in a sense, we could construct a black hole, and we could also construct a white hole, which is just the time reversed version. Yeah? Where we would go in what is the past with respect to the first picture. So in a sense, it is as you are saying. We have different possibilities for making the extension. Yeah, we have to decide either to do a black hole or a white hole, where we could also extend an exterior region with a black hole at one end and with a white hole at the other end. But one particular inner region is either a black hole or a white hole. Yeah, there is no way of, in a sense, realizing both things simultaneously for one interior region. That's impossible.
Okay, but in a black hole we cannot go in the past. But I'm just asking because if the T is now space-like, then why can't we operate with it like with a...
Yeah, but we cannot move on. So d by dt becomes space-like. That's correct what you are saying. But this doesn't mean that we can still move on a T-line. On the contrary, it means that then it's no longer possible for us to move on a T-line. Yeah? So we use the symbol T, but we should not associate it with the notion of time. It is no time. Yeah? Another remark, when we discuss question of this type, is a coordinate time-like or is it not time-like? We have to distinguish two things. which also becomes relevant for the rotating case, not for the non-rotating case. Do we speak about the lines, the t lines, or do we speak about the surfaces t equal constant? These are two different things. So the first question is, are the t lines time-like? That's the question we have just been talking about. Yeah, they are outside of the ergo region. They are time-like. Inside, they are space-like. And a completely different question is: are the surfaces t equal constant time-like? Space-like. Sorry, space-like. Are the surfaces t equal constant space-like? So can they be interpreted as snapshots of the world at a particular time? And actually, if you check this, oh, we could do this. I do this in a minute. When I have finished with this section, I do this actually. So we will see that the surfaces t equal constant are space-like everywhere outside of the horizon. Yeah. So even here, where the vector field d by dt is no longer time-like, the surfaces t equal constants are still space-like. That's possible because one is not perpendicular to the other, right? If the t lines were perpendicular to the surfaces, then one would immediately imply the other. But that's not the case here, and that's the reason why it's more complicated. So maybe I should have referred to the surfaces t equal constant when answering your question. This was actually would actually be more relevant than talking about the t lines. The t lines are relevant if I ask myself, can I move on this line? And the surfaces t equal constants are relevant if I ask the question, is t a reasonable time coordinate? Can I use it as for coordinatizing my space-time in a way that t equal constants are snapshots of the world? Yeah.
This is important to solve the Cauchy problem, right?
Yes.
The initial data
Yes.
was based
Yes.
on hypersurface
Yes.
and evaluated.
Yes. So the comment was, if I want to solve the initial value problem for some kind of wave equation, then I would need a space-like hypersurface for giving the initial condition. And the question is, if t equal constant, is this a reasonable initial hypersurface for my Cauchy problem, for my initial value problem? So here, outside of the horizon, t equal constant is a perfectly defined initial hypersurface. And actually, for those of you who know what a globally hyperbolic spacetime is, the spacetime outside of the horizon is globally hyperbolic. Yeah, not outside of the ergo region, outside of the outer horizon. So for the initial value problem, the horizon is the relevant thing, not the ergo region. Okay, but I also wanted to talk about the vector field d by d phi. So that's the other field associated with the symmetry of our spacetime. Yeah, d by dt means that the spacetime is stationary. Yeah, that the coefficients of the metric do not depend on t, means that the spacetime is stationary. And that it does not depend on d by d phi means that it is rotationally symmetric, about one axis, about our z-axis, not about any other axis. And also for this vector field, the question is reasonable and interesting is if this is always space-like, as we are used to it. So, or is also g phi phi becoming somewhere time-like? So again, we have to look at the metric. Oh my goodness. Let me see if I have a piece of chocolate with that one. Is that right? Okay, where's g phi phi? I hope it's, everything is still on the board. So it's, we can read g phi phi there. It's sine squared of theta. Then I have a bracket, r squared plus a squared plus 2mr a squared sine squared of theta over rho squared. Can this be smaller than 0? What would you say? Well, everything looks pretty much positive, right? Everything is fine. Would you agree? No. We have just been talking about the fact that we extend the r coordinate into the negative range. And you see, if r is negative, then this actually does become negative. Yeah? If r becomes negative, if r is very small and negative, then actually this, I need this here. I have to write it out. So this is irrelevant. This will certainly not change the sign. So I have r squared plus a squared What was rho squared? Rho squared was r squared plus a squared cosine squared of theta plus 2mra squared sine squared of theta. I've multiplied with rho squared. Rho squared is certainly not negative, so the sign is still in the same direction, okay? So let's see, what is this? If I send r to 0 from the negative, can one see this? So my claim is that for negative values of r near the ring singularity, this means, near the ring singularity. At the ring singularity I also have a squared cosine squared theta equal to 0. That was the essential point. So for a squared cosine squared theta equals 0. This means in the equatorial plane. Yeah, I am in the equatorial plane. Or, yeah, let me write it this way. That's the easiest way of doing it. So then I have r squared plus a squared times r squared. This goes to 0 if I approach the equatorial plane. And this approaches 1. It's 2mr a squared. And the question is this 0? Is it smaller than 0? So you see, if I have small values of r, this goes at least with r squared, but this goes with 1. So this term dominates. Yeah? So this here goes for r to 0. It goes to this goes to minus. No, I cannot write it in this way. This is negative. This is negative for small negative r. Yeah? If r is negative, then this term brings in a negative sign, so the whole thing would be smaller than 0 if the modulus of this term is bigger than this here. And the modulus is bigger than this term here for small values of r, because this begins with an r squared. So in the neighborhood of the ring singularity, r equals 0 and theta equal pi half is the ring singularity. In the neighborhood of the ring singularity, I have a region where d by d phi becomes time-like. Hey, what does this mean? d by d phi becomes time-like. d by d phi. Phi is a coordinate which parameterizes the circles around our axis. So these are closed lines. Yeah? The phi lines are closed lines. This means there are time-like curves which are closed. This means an observer can move along this world line because it's time-like, and he comes back to the same event. Not to the same point in space. That's what we are doing all the time. Yeah? When we are going home and coming back to the university, we always come back to the same point in space, but never to the same point in space-time. So time always increases along our world line. And we usually believe that it's impossible for us to really return to an earlier event. So we usually believe that it is impossible to return to an event, for instance, which lies before my own birth. Yeah? Because then there's this famous paradox. If I could return to an event which lies before I was born, I could kill my parents, and then I couldn't be born, and we would have a logical contradiction. So in the curve spacetime, so let me write the conclusion here. So we have time-like closed curves near the ring singularity, in a certain neighborhood of the ring singularity. Yeah, the question is, should this worry us? Well, again, we could say the ring singularity is hidden behind the horizon. If we do not have a naked singularity, if we are really in the case which I've written there, where we have a black hole, and we are an observer outside of the outer horizon, then we would never get any information from these closed time-like curves. But in principle, I could jump into the black hole, I could approach this area, and I could move along this time-like curve. It's not a geodesic, so I cannot move in free fall there. Yeah, I would need a kind of propulsion, a rocket engine or something like that, in order to stay on this circle. But I could do it with subluminal velocity, so it would be allowed for me. And the question is, should we be worried about this? This is one of the open questions associated with the Kerr metric. So this feature of these causality violating regions, as they are called, this occurs immediately when the A is not zero. Yeah, if I have a black hole with arbitrarily small but non-zero A, then we have this phenomenon. And we also have it, you see it from this expression, for the naked singularity case, right? So in the naked singularity case, it's even more troublesome, because then I could go to this region. I could make a few rounds on this closed time-like curve, and then I could go back to my friends who live far away from the black hole and could tell them what had happened to them and how I killed my grandfather and things like that before I was born. So then it's really accessible for me, and I could report to the outside world from this experience. So in this sense, the naked singularity case is certainly considerably worse than just the black hole case. But even in the black hole case, these causality violating regions, they are something which always worried me a little bit, and I have no clear answer how to live with this situation. There was a question?
Yes, so the problem with closed time-like curves, if the time that elapses until you return to the same space-time event is on a cosmological time scale, so then it would not be this paradox. Okay, this was an offer how one could evade the problem. So the claim was that the closed time-like curves should worry us only if it would be possible to go around on this circle during our lifetime, or a little bit more than our lifetime. But if it needs something like the whole age of our universe to go around, then there would be no trouble. But actually these it depends of course on the values for R and A. But if you insert values for A and M, if you insert values like for the black hole at the center of our galaxy, you wouldn't get times like the age of the universe. You would get fairly short times actually, like days or something like that, or hours. Yeah. So I think in this case this is no answer. So there are cosmological models where we have this type of closed time-like curves where you actually have to move very, very far away, and then you can come back to the same event. The Gödel space-time is of this type, just for those of you who have heard about this. There you have to move away. You have to go outside of a certain cylindrical domain, and only then can you come back to the same event. But that's different here. So these time-like curves, closed time-like curves near the ring singularity, they are fairly small. Yeah, actually you can do it in the equatorial plane, just a little bit outside of the ring singularity, and the circumference of the ring singularity is arbitrarily small. Yeah, so you can have arbitrarily short times. Yeah.
I mean, if you have the naked singularity, you could go there, you could return to Earth and tell everybody what it's like if you move on these time-like closed curves. But I mean, I could grab 10 people, jump into this black hole, and live at, I don't know, R is less than 0, as long as I live. And I mean, couldn't I then go to that singularity, move around those time-like closed curves, and go back to R is less than 0, and tell those 10 people who have jumped into the black hole with me?
Yeah. Okay, so the comment was that it is true that I cannot return to the outside world, outside of the horizon, and tell people about my experience, but I could take a few friends with me, and then spend a happy life for as long as nature allows on the other side of the horizon. Yeah, mine's the difference to Schwarzschild. I'm not pulled towards the singularity in this space-time. I can move through the ring singularity into the area r smaller than 0, and then I can move out to r equal minus infinity, where space-time is almost flat and the world is very similar actually to, might be, if it exists, might be quite similar to our world. And I could then just communicate with these people who have come with me. So it is true that I cannot report to the outside world where I originally come from, but I could live in another world, and I could then there report about my experience with a closed time-like curves. Yeah, that's true. So if this picture is true, that we can really move through the horizon, in principle at least, and that we have a nice and convenient environment there, then we might have similar problems than with reporting to our original outside world. Of course, the question is how big is the ring? Yeah. So is it really possible for me, I'm a fairly fat person, to go through this ring without being harmed? Yeah? So if this is, it depends on how fast the black hole is rotating. It depends on the mass, because it's the relative, the A over m is a relative, is an important thing. And it depends how fast the thing is rotating. Yeah, if it's very slowly rotating, if the A is small, then of course also the ring is very, very small. So it's a ring singularity, yeah? So the curvature becomes infinite on this ring. So if I come close to the ring, then I would be ripped apart by tidal forces. But if it's a big black hole with, I don't know, with millions or billions of solar masses, and if it's really quickly rotating, then I could quite comfortably move through this ring. And then one could really speculate that there are worlds on the other side, which are maybe quite convenient for living people. Yeah.
But if I was able to dive into the black hole and go through the ring singularity all the way to minus infinity, so r equals minus infinity, space-time is flat, and I can live there, and now the black hole loses angular momentum. What will happen to me? Will my world somehow be disconnected from the outside world? Will I be pulled into the r equals 0 singularity again? So the black hole slows down and loses angular momentum? What will happen to my world there?
Yeah. So the question was, what would happen for somebody who has moved to the region r smaller than 0, and now the black hole loses angular momentum? So in which way would my world then maybe be separated from the rest of the world? Yeah, actually we don't have a really good theory for time-depending black holes. Yeah, that's one of the programs many people are working on. It's associated with the notion of a dynamic horizon. Yeah, so we have a situation where really the black hole feature, which is coded into the horizon, this is time dependent, where something changes in the course of time. We have some rudimentary results in this direction, but no really full-fledged theory. So actually I'm not sure if one can answer this question on a basis of sound calculations.
And you can just imagine this through becoming narrow, and then somehow the two worlds getting disconnected.
Yeah, so to be honest, I have no idea what well, there's another thing associated with this. If you consider a black hole in its environment, if it is supposed to lose angular momentum, it must interact with some other parts. Then the assumption of being asymptotically flat is questionable. Yeah. So you would have embed your black hole into a world where you have also other masses. That's another issue which is investigated strongly right now. Goes under the name of deformed black holes or bumpy black holes, where you have other masses around the black hole, and this is now deforming the horizon. This is a completely isolated object, what we describe here mathematically. Yeah, it's asymptotically flat, so if you move away from this object, you never meet anything else. Yeah? The space-time then becomes flat. No other influence from other bodies. So that's a model, and it's completely time independent, it's stationary, so nothing changes in the course of time. So these highly idealized black holes, they are mathematically well understood. Yeah, we know what's going on there. This question which you are asking now, where you take the environment into account and interaction, is much more complicated.
So
and
there's something left for us to work it out.
there's a lot left to us for investigating this further, yes. Talking about this region R smaller than 0, I should have emphasized that if I am on this side of the singularity, then the singularity is naked for me. Yeah? Because the horizons are on the other side. Both horizons are on the other side. So if it's possible to move into the region R smaller than 0, and if this mathematical model describes the situation correctly, then actually there are naked singularities for these hypothetical observers on the other side of the thing.
But for real, so to say, naked singularity, it is both for this world and for that world, naked singularity.
Yes. Yeah. So if M is big, if A is bigger than M, then the singularity is naked for observers in both asymptotic regions. Yeah. So what actually is going on inside the horizon, in the neighborhood of the ring singularity, and how seriously this mathematical model should be taken, that's something which is under debate. Yeah, if we consider realistic black holes with environment, black holes which have evolved over time, which are not existing from minus infinity to plus infinity, then maybe the picture might change. So this is something one should keep in mind, that we have a kind of idealized situation. Okay, so this was d by dt and d by d phi. There was a point which was addressed where I said I will demonstrate this. Which was this?
The constant hypersurfaces. The t equals constant, but these are really space.
Okay, right. Thank you. Yes, I think I can just manage to do this today, and then we begin with the geodesics. Studying the geodesics is, of course, a little bit more complicated than it is for Schwarzschild. So we will spend some time then with the geodesics. Maybe I should leave the metric. Oops. So the next point is the hypersurfaces. T equal constant. So we can read from the metric. What's the metric on this hypersurface? It's of course a 3 metric. Yeah. This hypersurface is parameterized by r, theta, and phi. So it's 3-dimensional, and we will see what the metric is doing on this hypersurface. So the first term with the dt squared is gone, and the last term, the mixed term with dt d phi, is gone. And the rest is just rho squared delta dr squared plus rho squared d theta squared plus sine squared theta. Oops. R squared plus A squared plus 2mr A squared sine squared theta over rho squared d phi squared. So the question is this a positive definite metric? Yeah? Are all the coefficients positive? What would you say?
Probably depends on the region.
It depends on the region where we are. So we have to be careful with this term. Delta can be negative. Delta is negative between the horizons. Yeah? The horizons are the zeros of delta. So delta is positive for big R. It is negative between the two horizons, and then it's again positive. So you see this term here becomes negative between the horizons. But outside of the outer horizon, it is positive. Outside of the outer horizon, of course, also the R is positive. So this term is also positive. So this here is positive definite for R bigger than R plus. Yeah? So outside of the outer horizon, the hypersurface t equal constant is in fact space-like. And this has another interesting consequence, namely if I consider the vector field which is perpendicular to these hypersurfaces. That's not the vector field d by dt, it's a different vector field. If I consider this vector field, then that's a possible observer everywhere. Yes, everywhere. So we can define, I think I should take a different piece of chalk. Oops. A vector field U on this domain by two properties. The first property is that that G, U, dt, not dt, the other three, dr, G, U, d theta, G, U, d phi is equal 0. This means the vector field U is perpendicular to the hypersurface t equal constant. And the second property, GUU is minus c squared. So that's the first condition defines a vector field which is indeed time-like. Yeah? Because the hypersurface t equal constant is space-like, so what is perpendicular to this hypersurface must be time-like. And I can normalize it by this condition. And so this gives a distinguished vector field, time-like vector field outside of the horizon, which is time-like everywhere. That's a property which the vector field d by dt does not have. And this is called, U is called the four velocity of the zero angular momentum observers. Observers. Oops. They are often abbreviated SAMO. So there are at least two distinguished time-like vector fields. So one is if I have my surface t equal constant here, and if I have here the horizon, and here's the ergo region I should touch. Oops. So then I have d by dt. And I have, I should maybe draw it in this way because it's not perpendicular, so to indicate this. And this formula, this four velocity u of the zero angular momentum observers. Inside the ergo region, I have only my vector field u, but my vector field d by dt, of course, the vector field exists, but it's no longer associated with observers. So with this vector field u, I can cover the whole region up to the horizon. With a vector field d by dt, if I want to associate it with observers, I cover only the region outside of the stationarity limit surface. Okay, I think I should stop here. So we have hopefully got some ideas of what's going on in the Kerr spacetime, and we will then study in quite some detail the geodesics, the motion of light and of particles in the Kerr spacetime. See you next time.